Hello, and welcome back to Night Cosmos Sleep. Humanity is trying to understand a structure that we can never step outside of to observe. We can leave the ground, travel beyond the atmosphere, and send probes toward distant planets. But no matter how far they journey, every instrument remains inside the universe. There is no vantage point beyond it from which we can look back at space as a whole, measure its shape as we would measure an object placed before us, and clearly determine where the inside ends and the outside begins. Everything we know is built from the signals that reach us. Light reveals what stars and galaxies were once like. Radio waves carry traces from extremely distant regions of space. The motion of galaxies shows that the universe is expanding, and gravitational waves uncover collisions that no ordinary telescope could ever observe directly. Yet every signal has its limits. Light does not travel instantaneously, so when we look at a galaxy 1 billion light-years away, we do not see it as it exists today. We see an image that left that galaxy 1 billion years ago. The farther we look, the deeper we travel into the past. The universe revealed through our telescopes is not a single, simultaneous picture of all reality, but a collection of countless different moments. Beyond that visible range, there may be regions of space whose light has never had enough time to reach Earth. Other regions are being carried away by cosmic expansion so rapidly that signals emitted from them may never reach us at all. There is no physical wall blocking our view, yet a boundary still exists around what humanity can ever know. The observable universe is therefore like a room whose inhabitants can study it only through echoes. They cannot see the outer surfaces of the walls, nor can they know how large the greater structure containing the room might be. From the sounds that return to them, they can measure distances, infer shapes, and construct a remarkably accurate map. But that map is still created entirely from within. This leads to a question that sounds simple, but is extraordinarily difficult to answer. How different might a space appear from the inside compared with the shape it would have when viewed from the outside? In the theory of relativity, space and time are not a motionless background. They can curve, expand, and change under the influence of matter. The same structure of spacetime can therefore be described in very different ways depending on the observer's position. From the outside, a sufficiently large region of collapsing matter may form a black hole. A boundary known as the event horizon appears, beyond which no signal can return. To a distant observer, it seems to be a place where matter disappears from the accessible universe. But what would happen if the interior did not end at a point of infinite density? Some physical models suggest that when matter is compressed to an extreme degree, quantum effects that are not yet fully understood could prevent the collapse from continuing. Instead of reaching a singularity, matter might contract to a minimum state and then transition from collapse into expansion. If such a process is possible, the interior of a black hole may not simply be a place where every path comes to an end. It could open into an entirely new region of spacetime. To an observer who appeared much later, that first phase of expansion might resemble what we call the Big Bang. From this possibility emerges a bold hypothesis. Our entire universe may be the interior of a black hole formed within a larger reality. This idea does not suggest that galaxies are drifting through a dark cavity in the ordinary sense. If we truly lived inside such a structure, there would be no black wall visible at the edge of space, and no particular direction pointing toward the black hole's center. An observer would still see galaxies distributed throughout an expanding universe, just as telescopes record today. From the outside, the structure might be called a black hole. From within, it might be experienced as the entire universe. This is not yet a proven conclusion. No signal has been confirmed as coming from a parent universe. No telescope can look through an event horizon to directly examine what lies inside, and bounce models still depend on assumptions about matter at extremely high densities, and on a theory of quantum gravity that science has not yet completed. Recent observations have not been enough to change this. Some studies have detected an imbalance in the rotational directions of distant galaxies, raising the possibility that the universe may have a preferred direction or may once have possessed an overall rotation. However, these findings remain controversial and may be influenced by the regions of sky that were surveyed, the way samples were selected, or the methods used to process the data. An unusual signal is not evidence that the universe is rotating, and a rotating universe would not automatically mean that it exists inside a black hole. Every step in that chain of reasoning must be tested through independent observations. The value of the hypothesis does not lie in how strange or captivating it sounds, but in its ability to force science to reconsider deeper questions about the origin of space. Was the Big Bang truly an absolute beginning, or merely a transition? Do singularities exist in nature, or do they simply reveal that our current equations have reached their limits? And are black holes places where the history of matter ends, or only places where that matter disappears from the view of an outside observer? To move closer to these questions, we must first understand black holes as physics actually describes them. A black hole is not a hole carved into space, nor is it a machine that pulls in everything around it. It is a region where the structure of spacetime has changed so profoundly that no path remains, along which a signal can return to the outside. That very feature is what allows an object that seems to represent an ending to also be considered the beginning of an entirely different possibility. In popular imagery, a black hole is often portrayed as a dark abyss in space, constantly pulling everything toward itself. That image is powerful, but it can easily lead us to misunderstand what a black hole really is. It is not an empty cavity carved into space, nor is it a gigantic pit opening wide to swallow the stars around it. A black hole is a region where matter has altered the structure of space and time so profoundly that even light, though it moves faster than anything else in nature, no longer has a path that leads back out. To understand how such a region can exist, we must first think about gravity in a way that differs from our familiar experience on Earth. In everyday life, gravity seems like an invisible force that continually pulls objects downward. A stone falls from your hand, the moon moves around Earth, and Earth travels around the sun because objects with mass attract one another. This explanation works well enough in many ordinary situations, but when matter becomes extremely massive or is compressed into a very small region, gravity is no longer merely a simple pulling force. According to Einstein's theory of general relativity, matter and energy curve the space-time around them. Space and time are therefore not a fixed stage across which planets and stars simply move. The stage itself can bend, stretch, and change its rhythm under the influence of matter. A planet moves around the sun not only because an invisible force pulls it through empty space, but because it is following the most natural path through a region of space-time curved by the sun's mass. One way to imagine this is to picture a road passing through a landscape of hills and valleys. A traveler on the road may always feel as though they are moving forward, yet the entire route bends along slopes, dips, and curves in the terrain. Planets move through a similar kind of landscape, except that this terrain is not made of soil and stone. It is formed by the structure of space and time itself. The sun curves the space-time around it, Earth follows that curvature, and the moon travels through a region shaped by the combined influence of both Earth and the Sunday. Light is not exempt from this behavior. Although it has no rest mass, light still follows the shape of space-time. When a beam of light passes near a massive star, a galaxy, or a cluster of galaxies, its path can be bent. Astronomers have observed this effect in luminous arcs and stretched images of distant galaxies. There is no enormous piece of glass between us and those galaxies. Space itself acts like a lens, redirecting the light before it reaches our telescopes. Time also changes within a gravitational field. A clock placed near a massive object runs more slowly than a clock farther away. This difference does not exist only in abstract equations. Atomic clocks precise enough to detect it can measure variations in the passage of time between different elevations on Earth, and satellite navigation systems must continually correct for relativistic effects to prevent large positioning errors. This shows that space and time are truly flexible parts of nature. A black hole forms when that distortion becomes extreme. Most black holes, with masses comparable to stars, are thought to form from the collapse of very massive stars. Throughout most of its life, a star maintains its shape through a long-lasting balance between two opposing tendencies. Gravity continually tries to pull all of the matter inward, while nuclear reactions in the core produce energy and pressure that push outward. This balance can keep a star stable for millions or even billions of years. Inside the core, lighter atoms combine to form heavier ones, releasing energy in the process. In sufficiently massive stars, this occurs through several stages, creating different layers of elements from the outside toward the center. But this source of fuel does not last forever. When the core can no longer generate enough energy to resist gravity, the balance begins to break down. Gravity does not suddenly need to become stronger. It simply loses the outward pressure that had been opposing it. The stellar core begins to contract. Matter is squeezed into a smaller volume, and both temperature and density rise rapidly. The outer layers may be blasted away in a stellar explosion, while the remaining core continues to collapse beneath its own weight. The fate of the core depends on how much matter remains. If its mass stays below a certain limit, quantum effects can produce enough pressure to halt the collapse, leaving behind a neutron star. Matter inside a neutron star is compressed so intensely that even a very small amount could weigh as much as a mountain. But if the core is too massive, even this supporting mechanism is no longer strong enough to keep it stable. The collapse continues, and an event horizon begins to form. The phrase event horizon may suggest a visible boundary, but in reality it is not a material surface. It is not a hard shell, a membrane, or a dark wall surrounding the black hole. Someone crossing that boundary would not necessarily collide with anything at all. The event horizon simply marks the point where the structure of space-time has changed so completely that every outward path no longer leads back to the rest of the universe. A useful comparison is a river flowing toward a waterfall. Far from the falls, the current moves slowly enough that a strong swimmer can still make their way upstream. As the waterfall draws closer, the current becomes more powerful. There may be a point where the speed of the water exactly matches the swimmer's maximum speed. Once the swimmer crosses that point, they can still turn toward the upstream direction and continue swimming. But no matter how hard they try, the current will carry them toward the falls. In this image, the flowing water represents the way space-time is directed inward toward the interior of a black hole, while the swimmer's maximum speed represents the speed of light. Outside the event horizon, light can still travel away if it is emitted in the right direction. Once it has crossed the boundary, light does not become slower. Instead, every path available to it leads farther inward. What makes the event horizon extraordinary is not the presence of an object located there, but the way the possibilities of the future change. Outside a black hole, a spacecraft can turn around, accelerate, and move away if it still has enough energy. Inside the horizon, moving deeper inward is no longer a choice that can simply be refused. It becomes more like the way everyone inevitably moves toward tomorrow. A traveler may turn around, transmit a signal, or fire their engines in any direction, but every possible future path continues to carry them farther inside. For the person who is falling, the moment of crossing the horizon would not necessarily be accompanied by any obvious sign. If the black hole were large enough, the tidal forces at the boundary might not yet be strong enough to create an immediate sensation of anything unusual. There would be no impact, no membrane to break through, and no line of light marking where the outside ends. The traveler would simply continue in free fall, while the laws of physics around them would still appear to function normally. From far away, however, the scene would look very different. Light emitted by the falling object would have to climb outward through an increasingly powerful gravitational field. As it did so, its wavelength would stretch, its energy would decrease, and the signals reaching the distant observer would arrive more and more slowly. The object would appear to move more gradually as it approached the horizon, its color shifting toward red before fading until it could no longer be detected. It would not truly stop on an invisible shell. The light carrying information about it would simply become increasingly unable to escape. These effects can easily create the impression that a black hole possesses a gravitational pull far greater than anything else in the universe. Yet, at a sufficient distance, the gravitational field of a black hole is no different from that of any other object with the same mass. It does not reach across space to drag everything toward itself, nor does it continuously consume nearby planets and stars simply because they happen to be there. If the Sun could somehow be replaced by a black hole with exactly the same mass, without changing the positions or velocities of the planets, Earth would not immediately be pulled inward. Its orbit would remain essentially unchanged because the amount of mass at the center of the solar system would still be the same. What would quickly make Earth uninhabitable would be the disappearance of sunlight and warmth, not the sudden appearance of a stronger gravitational force. An object becomes endangered only when it travels close enough, much as a star, planet, or neutron star can strongly influence objects in its immediate surroundings. What distinguishes a black hole is that all of its mass has been concentrated into an extremely small region, making the curvature of nearby spacetime far more intense. For this reason, the image of a black hole as a cosmic vacuum cleaner is not particularly accurate. A vacuum cleaner creates a flow of air that carries matter toward it, while a black hole simply causes objects to move along the shape of spacetime created by its mass. The degree of compression required to form a black hole can be imagined through a few numbers. The Sun currently has a diameter of nearly 1.4 million kilometers. If all of its mass were compressed into a region with a radius of roughly 3 kilometers, an event horizon would form. This means that a star hundreds of times wider than Earth would have to be compressed into a region only a few kilometers across. For Earth, the difference is even more extreme. If the planet's entire mass were preserved but compressed enough to become a black hole, the radius of its event horizon would be only about 9 millimeters. Earth's oceans, crust, mantle, and iron core would all have to fit inside a region smaller than many familiar objects held in the hand. Nothing like this could happen to a planet through any ordinary natural process, but the number reveals that mass alone is not what determines whether a black hole forms. That mass must be concentrated into a region so small that the curvature of spacetime no longer permits light to escape. An object can contain an enormous amount of matter without becoming a black hole if that mass is spread across a sufficiently large volume. When the same amount of matter is compressed more deeply, however, an event horizon may appear. This is why black holes can exist in many different sizes. Some weigh only several or several dozen times as much as the Sun and are born from stars. At the centers of many galaxies are supermassive black holes, with masses millions or even billions of times greater than the Sunday. Despite their enormous differences in mass and size, all black holes share one basic feature: a boundary beyond which information cannot return. Outside and near that boundary, general relativity describes black holes with remarkable precision. Light bends in ways that can be calculated, time passes differently depending on distance, and objects orbiting a black hole follow paths that agree with theoretical predictions. But when the equations are extended deeper into the interior, they lead to a result that is far more difficult to interpret. In the classical description, matter continues to collapse until its volume approaches zero, while its density and the curvature of spacetime approach infinity. This limiting state is known as a singularity. The name can make it sound like a physical object that science already understands, but a singularity more accurately marks the point where the equations no longer provide a complete physical description. When a theory produces infinite values, it is possible that nature truly contains such an extreme state. It is also possible that the model has been pushed beyond the range in which it remains valid. Throughout the history of science, infinities have often signaled that a deeper layer of physical law has not yet been included. General relativity describes gravity extraordinarily well, but it is not a quantum theory. In regions where matter is compressed to immense densities and dimensions become extremely small, quantum effects may no longer be ignored. The difficulty is that science does not yet possess a complete and experimentally verified theory of quantum gravity. General relativity explains the universe on large scales, from planetary motion to the structure of galaxies and the cosmos itself. Quantum physics describes the world of tiny particles with extraordinary accuracy, yet when intense gravity and quantum effects both become important, these two frameworks have not been fully connected. For that reason, what happens in the deepest region of a black hole remains beyond our certain understanding. A singularity may exist exactly as the classical equations predict. Matter may instead reach some limit and enter a state that general relativity cannot describe. It is also possible that the structure of space and time changes in an entirely different way at extremely high densities. This uncertainty does not mean that everything we know about black holes is merely speculation. On the contrary, many predictions concerning the region outside the event horizon have been confirmed through observation. We have seen light bend, tracked stars orbiting invisible concentrations of mass, observed matter heating as it falls toward black holes, and detected ripples in spacetime created when two black holes merge. The mystery is no longer whether black holes exist, but what truly happens after every signal has crossed the horizon. It is here that the image of a black hole as a simple pit begins to dissolve. It has no mouth, no bottom in the familiar sense, and it is not a solid object resting in empty space. A black hole is a structure of space-time in which the meaning of direction, distance, and the future has been altered by extreme gravity. If the event horizon is not a wall, someone passing through it might not immediately realize that they had crossed inside. If the interior region were large enough, they could still observe light, measure time, and experience their surroundings for a certain period. From a local point of view, there would be no sign announcing that all the space around them now lay beyond a boundary that could never be crossed in reverse. This opens a deeper question. If an enormous region of space can exist beyond an event horizon, what would those living within it see? Would they see a dark shell surrounding them, or only open space, light, and objects moving according to their own physical laws? Would they know that they were inside a black hole? Or would the idea of being inside have meaning only to an observer located somewhere else? A black hole sends no light from the region hidden behind its horizon, yet it leaves unmistakable traces throughout its surroundings. Its mass changes the orbits of stars, heats gas and dust, bends light from more distant objects, and causes the structure of spacetime itself to tremble when two black holes collide. Humanity cannot see the darkness within directly, but we have learned to recognize it through everything nearby that moves and shines. An object that emits no light might seem to leave nothing for a telescope to observe. If it were suspended in empty space, completely dark and reflecting no signal at all, we might imagine that it would vanish from every map of the sky. Yet in the universe, an object does not need to shine in order to reveal its presence. Its mass can still set other objects in motion, bend the path of light, heat nearby gas, and create ripples in spacetime. Black holes are discovered not by looking directly into the darkness, but by observing what happens around it. One of the clearest examples lies at the very center of the Milky Way. From Earth, this region is hidden behind thick clouds of dust that visible light can barely penetrate. Astronomers must observe it at other wavelengths, particularly in infrared and radio waves, to see through the dust and track the motion of stars orbiting very close to the galactic center. Over the years, those stars have revealed that they are anything but still. They move at tremendous speeds around a small region that gives off almost no light. Some complete their orbits quickly enough for astronomers to follow nearly their entire paths within a few decades. As the position of each star is recorded year after year, curved orbits gradually emerge, like invisible lines being drawn around a point that no telescope can see directly. A leaf circling on the surface of a stream can reveal the current, even when the water itself is nearly transparent. The stars at the center of the Milky Way serve a similar purpose. They respond to an extraordinarily powerful gravitational field, and their motion allows scientists to calculate the mass of the object at the center. Measurements show that matter equal to roughly 4 million times the mass of the Sun is concentrated within an extremely small region of space. No ordinary star cluster could remain stable while containing so much mass in such a confined volume without producing other detectable signs. The best explanation is a supermassive black hole. This object is known as Sagittarius A, and it lies about 26,000 light-years from Earth. That distance is far beyond anything we can experience in ordinary life. Yet on the scale of the Milky Way, Sagittarius A times is still part of the galaxy we call home. Light and radio waves leaving the galactic center must travel for 26,000 years before reaching observatories on Earth. Every image and signal received today therefore shows that region as it existed 26,000 years ago. Astronomers do not see a black sphere resting at the center of those orbits. What they see are stars being guided by an invisible mass. As their orbits are measured with greater precision, the limits placed on the size of that central mass become increasingly strict. If 4 million suns were spread across a much wider region, the stars would move differently. The fact that they orbit rapidly around such a compact point shows that the mass must be extraordinarily concentrated, exactly as expected for a black hole. This is a familiar method in astronomy. We often discover objects through their effects on the surrounding environment rather than through their own light. A planet beyond the solar system may be found because it causes its host star to wobble slightly. Dark matter is inferred from the way galaxies rotate and the way light bends around them. Black holes are recognized through the same basic principle. When an invisible object continually leaves a measurable gravitational signature, that signature can be used to infer what is hidden from view. A black hole, however, does not always lie within a completely dark region. When gas, dust, or material from a nearby star falls toward it, the surrounding area can become one of the brightest places in the universe. Matter does not usually plunge straight toward the event horizon along a simple path. It carries sideways motion, causing it to orbit the black hole and form a flattened structure known as an accretion disk. Within this disk, the layers of gas do not all move at the same speed. Matter closer to the black hole orbits faster than matter farther away, producing collisions, turbulence, and friction on an enormous scale. Energy from orbital motion is gradually converted into heat. Before crossing the event horizon, the gas can become hot enough to emit intense visible light, ultraviolet radiation, or X-rays. The black hole itself remains dark, but the environment around it can shine more brightly than billions of stars combined. This is why illustrations of black holes often show a glowing ring or disk surrounding a dark central region. That light does not come from inside the event horizon. It is produced by matter that remains outside, where photons can still escape and travel toward our telescopes. The luminous region reveals matter losing energy, heating up, and slowly approaching a boundary from which no signal can ever return. Not every black hole possesses a brilliant accretion disk. If the surrounding region is nearly empty, a black hole may remain quiet and extremely difficult to detect. Sagittarius A times is not currently consuming as much material as some black holes at the centers of highly active galaxies, so it is relatively dim for an object of its mass. Even so, the small amount of hot gas nearby still emits radio signals, allowing us to observe the region close to its event horizon. In other systems, a black hole may orbit an ordinary star and draw material away from it. Gas is pulled free, spirals into a disk, and heats up before falling deeper inward. X-rays from this region can be detected by satellites. By combining X-ray observations with measurements of the companion star's motion, scientists can estimate the mass of the dark object. If it is too massive to be a neutron star yet emits no light like an ordinary star, a black hole becomes the most likely explanation. Observations like these gradually transformed black holes from mathematical predictions into astronomical objects that could be studied. Even stronger evidence emerged when humanity began to measure not only matter moving around black holes, but also the ripples produced when two black holes collided. According to general relativity, moving objects can generate gravitational waves, much as an object can create ripples across the surface of water. In most situations, these waves are far too weak to measure. Earth produces gravitational waves as it orbits the Sun, but they are so faint that no current instrument can detect them. When two massive black holes orbit each other, however, the situation becomes very different. Each black hole strongly curves the spacetime around it. As the two objects spiral through increasingly tight orbits, the system releases energy in the form of gravitational waves. This loss of energy causes the distance between them to shrink, their orbital speed to rise, and the frequency of the waves they produce to increase. Their final revolutions occur with extraordinary speed before the two event horizons merge into a single, larger black hole. This event does not create sound traveling through the vacuum of space, but when the data are converted into frequencies that the human ear can hear, the signal often resembles a brief tone rising in pitch. In a fraction of a moment, part of the system's mass is transformed into gravitational wave energy. Those ripples spread outward in every direction, passing through stars, planets, and the empty spaces between galaxies with almost nothing to obstruct them. When a gravitational wave passes through Earth, it compresses space in one direction while stretching it in the perpendicular direction, then rapidly reverses the pattern. The change is extraordinarily small, far less than the width of an atom when measured across the length of the detector. Observatories such as LIGO use long arms, laser beams, and highly sophisticated vibration isolation systems to detect this faint distortion. A signal consistent with the merger of two black holes does more than reveal that something extremely massive has collided. The shape of the wave contains information about the masses, spins, and orbital motion of the two objects. When compared with simulations based on general relativity, the data match the process of two black holes drawing closer, merging, and settling into a new black hole. This is an entirely different form of observation from detecting light because no glowing gas or companion star is required. The structure of spacetime itself carries the signal to Earth. The mergers we have detected also show that black holes are not motionless objects existing in isolation. They can form pairs, orbit one another, gain mass, and change over time. Some black holes may be born from massive stars and later merge into heavier objects. Events like these may help explain how black holes grew throughout the history of the universe. Although stellar orbits, X-rays, and gravitational waves all provide powerful evidence, scientists still wanted to observe the region near an event horizon with enough resolution to see the shadow created by a black hole. The challenge lies in the target's apparent size. Even a supermassive black hole looks extraordinarily small when viewed from millions of light years away. Resolving such a structure requires a telescope far larger than any single dish humanity could ever build. The solution was not to construct an enormous telescope out of physical material, but to connect observatories located far from one another. The Event Horizon Telescope is a network of radio telescopes positioned across many regions of Earth. When these observatories study the same source at the same time, and their data are synchronized using extremely precise atomic clocks, they can function as parts of a single virtual telescope. The distance between the observatories determines the system's effective resolution. With telescopes spread across several continents, the baseline can extend across nearly the entire diameter of Earth. This allows the Event Horizon Telescope to achieve the resolution needed to study a region comparable in size to the event horizon of a supermassive black hole. The first target to produce a famous result was the black hole at the center of the galaxy M87. This galaxy lies far beyond the Milky Way, but its central black hole has a mass of roughly 6.5 billion suns. That immense mass creates an event horizon large enough to be studied even across such a distance. M87 times is also surrounded by matter that produces powerful radio emissions, making it a suitable target for the telescope network. The observation was nothing like taking a photograph with an ordinary camera. Each observatory collected extremely faint radio signals while recording an enormous amount of data, along with the precise arrival time of every signal. The total data gathered during the M87 times observing campaign amounted to roughly 5 petabytes. 1 petabyte is equal to 1 million gigabytes, so this volume of information was far too large to be transferred quickly over the internet between the observatories and the processing centers. The hard drives had to be physically transported from many different locations to the facilities where the data would be combined. At some remote observatories, weather and geography delayed the transportation process even further. Once the data arrived, research teams had to synchronize, calibrate, and combine them using complex computational methods. Earth rotated throughout the observation, changing the relative positions of the telescopes and allowing the network to collect additional information about the source. From these scattered signals, algorithms reconstructed the kinds of structures capable of producing the observed data. Several teams used independent processing methods to reduce the risk that a single algorithm might impose a particular shape on the result. After years of testing, comparison, and error analysis, the image was released in 2019. It revealed an uneven ring of light surrounding a dark central region. This was not a photograph of the black hole's surface, because a black hole has no luminous surface from which light can reflect. The darkness in the center is commonly known as the black hole's shadow. It forms because many rays of light passing too close are captured by the black hole, while others are strongly bent by gravity before escaping. The shadow is larger than the event horizon itself in a simple geometric sense, because light near a black hole does not travel in straight lines. Some rays can circle around the black hole before leaving the region near the horizon. The intense gravitational field bends images of matter behind and around the black hole, helping to create the luminous ring. The uneven brightness of that ring is also connected to the extremely rapid motion of the gas. Material moving toward the observer can appear brighter because of relativistic effects. The most important information was not contained in the color assigned to the image, but in its shape, size, and structure. These features agreed with predictions for a black hole whose mass had already been estimated through other methods. An object once inferred only through motion and radiation had now produced a shadow that could be reconstructed from observational data. After M87, attention returned to Sagittarius A, the black hole at the center of the Milky Way. It is much closer to Earth, yet it presented a different kind of difficulty. Sagittarius A times has a mass of about 4 million suns, making it more than 1,000 times less massive than M87. Because it is physically smaller, matter near it completes orbits and changes in brightness over much shorter periods. Observing M87 times could be compared to photographing a relatively stable object over several hours. Sagittarius A times was more like a target changing while the camera was still collecting light. As observatories across Earth recorded data simultaneously, the gas around the black hole continued to move. These rapid variations made the signals difficult to combine because the observing technique generally assumes that the target does not change too dramatically during the period of data collection. Scientists had to develop processing methods suited to a rapidly changing source, test many different models, and identify stable features that continued to appear throughout the data. The result was released in 2022, revealing a ring-like structure surrounding a dark region with an overall shape consistent with the predictions of general relativity. The two images are not identical. M87 times and Sagittarius A times differ enormously in mass, in the rate at which their surrounding matter changes, and in their galactic environments. Even so, when their scales are adjusted, both shadows agree with the geometry expected around a black hole. This similarity suggests that the same laws of gravity can describe objects whose masses differ by more than a factor of 1,000. The image of Sagittarius A times also connected two forms of evidence that had been collected over many years. Stellar orbits showed that a mass of roughly 4 million suns lies at the center of the Milky Way, while data from the Event Horizon Telescope revealed a shadow with the size expected for a black hole of that mass. Motion on a larger scale and structure near the horizon both pointed toward the same explanation. As impressive as these achievements are, they still have clear limitations. The Event Horizon Telescope cannot see through the event horizon. The dark region in the image is not a window into the interior, but the signature of light that has been captured or redirected. Everything recorded comes from outside the horizon, where signals still have a chance to reach Earth. The images, therefore, do not reveal where matter ultimately goes after crossing the boundary. They do not show a singularity, nor do they confirm that a singularity truly exists. They cannot reveal a bounce, a new region of space, or a child universe. Every question concerning the deep interior remains beyond the direct reach of these images. Gravitational waves do not overcome this limitation either. Signals from mergers allow scientists to test how two black holes move and how the newly formed black hole settles into stability, but whatever happens deep inside the horizon remains hidden. Stellar orbits, accretion disks, and radiation all tell the story of how a black hole affects its external environment, not of any world that might exist within it. This creates an important boundary between observation and hypothesis. The existence of black holes is supported by several independent forms of evidence. Humanity has tracked stars orbiting them, detected hot gas before it falls inward, measured gravitational waves from mergers, and reconstructed the shadows of two supermassive black holes. Each method relies on a different physical phenomenon, yet all of them agree with the same underlying description. The possibility that our universe exists inside a black hole belongs to a different level of speculation. No image of M87 times or Sagittarius A times reveals a universe existing beyond the horizon. The reality of black holes does not mean that they create child universes. The success of general relativity in describing the exterior does not mean that our current equations can explain the extreme conditions deep within. The data we already possess allow these questions to be asked on firmer ground. Black holes are no longer imaginary objects, introduced merely to make a cosmic story feel mysterious. They are objects with measurable masses, sizes, spins, motions, and surrounding environments. It is precisely because science has learned so much about their exterior regions that it can begin to ask where their interior geometry might lead. As the masses and dimensions of black holes have been measured with increasing precision, a remarkable resemblance has begun to appear within the equations. The mathematics used to describe spacetime inside certain black holes can share features with the mathematics used to describe an evolving universe. This resemblance is not evidence by itself, but it is enough to reverse the familiar question. Instead of asking only where black holes exist within the universe, humanity has begun to wonder whether the entire universe might itself lie inside a similar structure. Human beings often speak of the universe as though it were an object that has already been seen in its entirety, with a clearly defined size, shape, and boundary. Yet everything telescopes have ever recorded belongs only to a finite region around us. This region is known as the observable universe, and that name contains an important limitation. It does not mean the entire universe. It refers only to the portion of space from which light or other signals have had enough time to reach an observer on Earth. The universe is about 13.8 billion years old. If space had remained still, we might imagine that the oldest light we receive could have traveled from no more than 13.8 billion light years away. But space has not remained still throughout that time. While light was traveling toward us, the distances between large regions of the universe continued to increase. As a result, the places that emitted those signals long ago are now much farther away than the distance the light originally had to cross. This is why the present-day radius of the observable universe is greater than 13.8 billion light-years. The most distant objects from which we can receive signals are now located much farther away because the space between them and Earth expanded throughout the light's journey. This difference does not exist because light once traveled faster than nature's speed limit. It exists because distance is not measured against a fixed background. In cosmology, the scale used to measure distance changes with time. The boundary of the observable region is therefore not a wall located somewhere beyond the farthest galaxies. There is no layer of dark material surrounding reality and preventing light from traveling any farther. What exists is a limit on information. Light from more distant regions has not yet had enough time to reach us, or may never arrive because the expansion of space is accelerating. We might imagine someone standing in the middle of a vast landscape covered in fog. Their vision extends only to a certain distance, but the line where the scenery disappears is not the edge of the land. It is simply the limit at which light can reach the observer's eyes under those conditions. Beyond the fog, there may be valleys, cities, or territories far larger than anything they can see. The person standing within it cannot observe those places, but they also have no reason to conclude that everything ends where their vision fades. The observable universe has a similar quality, although its limits are created not by fog, but by the age of the universe, the speed of light, and the history of cosmic expansion. We live at the center of the region visible to us, but this does not mean Earth occupies the true center of the entire universe. An observer in a very distant galaxy would also see themselves at the center of their own observable region. Every location has its own horizon, defined by the signals capable of reaching it. The idea of a horizon in this context is not entirely unfamiliar to the physics of black holes. A black hole has an event horizon, a boundary that prevents signals from returning from the interior to the space outside. The universe also possesses horizons related to distance, time, and the rate of expansion. In both cases, certain regions cannot send information to a particular observer. This similarity has led some physicists to ask whether the two structures might be connected at a deeper level, but the resemblance must be treated carefully. A black hole's event horizon and a cosmic horizon are not automatically the same kind of boundary. They arise within different geometries, depend on different physical conditions, and may change in different ways. The fact that both limit information merely opens a path for comparison. It does not prove that the universe is a black hole. Just as the fact that two rivers both have banks does not mean they are the same body of water. An event horizon is defined by a region of spacetime from which no signal can escape to the outside indefinitely. An object that has crossed this boundary may continue moving through the interior, but every possible path into its future no longer leads back to the external region of space. A cosmic horizon, by contrast, is related to regions whose signals have not yet reached us, or can no longer reach us because space is expanding. This boundary is not necessarily fixed, nor does it surround us like the material surface of a sphere. Despite their differences, both horizons point toward an unavoidable truth. An observer does not have access to the whole of reality. Some places exist beyond their ability to receive information. This changes the way a structure can be described. An observer outside a black hole and another falling within it do not share the same picture of time, light, and the paths that remain possible. In a similar way, someone living in an expanding universe can construct a map only from the signals that have reached their location. From this limitation, a bold idea began to take shape. In 1972, physicist Raj Kumar Pathria published a paper in the journal Nature, proposing that a closed universe could be described as the interior of a black hole existing within a larger space. This was not a claim that telescopes had detected a black hole wall surrounding us. It was a proposal about the geometry of space-time, based on a relationship between a cosmological model and the internal structure of a black hole. What makes the idea remarkable is the way the same reality might be understood differently depending on the observer's position. From the outside, a large mass of matter may be collapsing under gravity. Once the mass is compressed far enough, an event horizon forms and hides the interior from everything beyond it. An external observer would see only the formation of a black hole and its gravitational effects. But when spacetime is described from within, the picture may be different. Instead of seeing a small object resting inside a larger space, an observer living in the interior might experience space expanding around them. Distances between regions could change over time, matter could be distributed throughout an enormous volume, and the outer horizon would not appear as an observable wall. This difference may sound contradictory, but relativity has repeatedly shown that different observers can describe the same process in very different ways. Time does not pass at the same rate everywhere. Distance is not an entirely unchanging quantity. An event may occur within a finite amount of time for someone who is falling, while its signals appear increasingly slow and faint to someone watching from far away. What Pathria suggested was the possibility that the interior of a gravitational structure could possess the geometry of a universe. From the outside, it would be a black hole. From the inside, it could be the entirety of space accessible to an observer. This idea does not require those living within it to see a dark sphere surrounding them. On the contrary, if the geometry were suitable, they might simply observe regions of matter moving apart within a space that has its own history of evolution. One reason the hypothesis continues to attract attention is the comparison between gravitational size and the amount of matter contained within the observable universe. For a non-rotating, uncharged object, the Schwarzschild radius depends directly on its mass. As the mass increases, the size of the corresponding horizon also grows. If enough matter is concentrated within that radius, a black hole can form. When researchers place estimates of the mass or density of the observable universe into gravitational comparisons, they find that the relevant scales can lie surprisingly close to one another. The size of the observable region and the gravitational scale associated with the matter and energy it contains are not as widely separated as intuition might suggest. This proximity raises the question of whether the universe could be described as a structure resembling a black hole. However, this simple comparison can easily be misleading. The Schwarzschild radius is derived for a spherical, non-rotating object embedded within a relatively simple external spacetime. The universe is not a stationary sphere of matter suspended in empty space. It is expanding, contains radiation, dark matter, and dark energy, and has no observed external region that could serve as a background for the structure as a whole. The mass of the universe is also not easily defined in the same way as the mass of a star. In a dynamic spacetime, energy, pressure, and curvature are connected in far more complicated ways. Dark energy not only contributes to the universe's overall energy content, but is also associated with its accelerating expansion. For that reason, taking an estimated value, inserting it into the Schwarzschild radius formula, and concluding that the universe is a black hole would leave out most of the physics that must be considered. Two quantities falling near the same scale can be suggestive, but they are not evidence. In science, many values can happen to lie close together without sharing the same origin. To turn this resemblance into a convincing model, it would be necessary to show that the same system of equations can consistently describe the history of cosmic expansion, the distribution of matter, the cosmic microwave background, and the many other observations already explained quite successfully by the current cosmological model. Part of what makes the hypothesis difficult to imagine is that human beings usually picture a black hole from the outside. We think of a dark region among the stars, surrounded by a horizon, with a center hidden somewhere deep within. If the universe existed inside such a structure, intuition might lead us to imagine galaxies drifting through an enormous black sphere, with some visible boundary in the sky marking the edge of the black hole. But an observer living inside would not necessarily see that shape. A horizon is not a glowing wall that telescopes can identify. It is simply a limit defined by the paths that light is able to follow. If the observer's entire region of space lies beyond the horizon, then every instrument they build also exists within the same structure. They cannot send a detector outside and have it return with a report of the overall shape. The space around them could still appear immense and nearly uniform. Galaxies might lie in every direction. Light could travel between nearby regions, planets could continue orbiting stars, and the local laws of physics could operate normally. There would be no reason for someone on a planet inside to feel that they were living within a hole. Even the idea of a center becomes difficult to apply. In the familiar picture, a black hole has a center because collapsing matter appears to move toward a central region. But a homogeneous, expanding universe reveals no special location among the galaxies. From any galaxy, an observer can see more distant galaxies moving away. This does not make every galaxy the true center of the universe. It simply reflects the fact that distances within space are increasing everywhere. The most familiar illustration is a collection of small dots drawn on the surface of an inflating balloon. As the balloon grows, every dot sees the others moving away. No point on the surface can indicate another point on that same surface and identify it as the center of the expansion. The geometric center of the balloon lies in the three-dimensional space outside the two-dimensional surface on which the dots exist. This image helps explain why cosmic expansion does not require a center located somewhere within the observable universe. Any two sufficiently distant galaxies can move apart because the space between them is expanding. No galaxy needs to be flying outward from a central point of explosion. Space is not expanding into a pre-existing emptiness in the way an inflating balloon occupies more room inside a building. Even so, the balloon is only an analogy. Our universe has three spatial dimensions, not the two-dimensional surface of an object embedded in some larger space that human beings have observed. The center of the balloon in the illustration should not be interpreted as a real location outside the universe. The comparison is meant only to show that a space can expand without requiring a center within itself. This caution becomes especially important when connecting the idea to black holes. An astronomical black hole forms when matter collapses within a space that already exists. We can identify the external region, observe matter falling inward, and define a horizon around the central mass. The universe in the Big Bang model, by contrast, is not described as matter exploding into empty space. There is no pre-existing room for the universe to occupy. The geometry of space itself changes with time. The Big Bang was therefore not an explosion that occurred at one particular point within the universe. In the Standard Model, the early hot and dense state existed everywhere throughout the space that later developed into the observable universe. Every galaxy today originated from regions that were once much closer together, but no galaxy can be identified as occupying the location where an original explosion took place. This is a major difference between saying that the universe resembles the interior of a black hole and simply saying that the universe is one enormous black hole. The second statement can easily create the image of the universe as a single object already resting within a larger space, with a center, an edge, and a size that could be measured from outside. The first is more careful because it refers to a possible resemblance or connection between different spacetime geometries. Turning that possibility into a complete model requires overcoming a major obstacle. Classical general relativity predicts that matter collapsing inside a black hole will continue toward a singularity. There, density and spacetime curvature rise toward infinity, while the equations lose their ability to provide an ordinary physical description. If the singularity is an absolute endpoint, then no new space opens beyond it. There is no continuing history, no expansion, and no child universe able to develop. The interior of the black hole simply leads to the point where every current description comes to an end. For this reason, the idea of a universe being born inside a black hole cannot rely only on similarities between horizons or gravitational scales. It requires a mechanism explaining why collapse does not end at infinite density. Something must change when matter is compressed to an extreme limit. Quantum effects may become strong enough to resist further contraction. The structure of spacetime may no longer remain continuous in the way classical equations assume. Or a deeper theory may replace the idea of a singularity with a finite physical state. At present, none of these possibilities has been directly confirmed. Science has not seen inside an event horizon, measured matter in the region of a singularity, or completed a theory of quantum gravity that has passed every experimental test. What does exist are models suggesting that collapse may not necessarily continue toward infinity if new laws emerge at extremely high densities. It is at this boundary that the question of the universe and black holes begins to change. Instead of asking only whether the two structures resemble one another, we must ask, what happens when contraction reaches a point where general relativity is no longer sufficient? If the singularity is not the end, matter may slow before reaching infinite density. If the contraction can be halted, the motion may reverse. Space that was once compressed could begin to expand, and from the inside, that process might take the form of a universe being born. That transition from contraction to expansion is known by a simple name: a bounce. When people hear the words Big Bang, many imagine a tiny point of matter suspended in empty space, suddenly exploding and sending galaxies flying in every direction. The image is intuitive, but it does not accurately reflect what the cosmological model describes. The Big Bang was not an explosion that occurred at a particular location in space, because according to our current understanding, space did not exist as an empty room for matter to explode into. Instead, the distances between regions of space changed, allowing a universe that was once hotter and denser to gradually become larger, cooler, and structured as it is today. The clearest trace of this process can be found in the motion of galaxies. On sufficiently large scales, most distant galaxies are moving away from us, and galaxies at greater distances generally recede more rapidly. This does not necessarily mean that they are flying through a fixed background of space like fragments from an explosion. An important part of the motion we observe comes from the fact that distances within space itself are increasing. Light traveling through expanding space is also stretched to longer wavelengths, leaving behind the redshift that telescopes can measure. If we imagine this history running backward, galaxies that are now far apart would gradually move closer together. Galaxy clusters would become more tightly packed, the density of matter would rise, and radiation would grow hotter. Tracing the universe far enough into the past brings us to an era before stars, planets, or neutral atoms existed. Matter was present as a hot mixture of particles and light. Farther back still, the temperature and density continue to rise until our familiar descriptions of matter can no longer be applied in the usual way. The Big Bang is therefore not merely a story about a single moment in the distant past. It is a conclusion built by tracing backward from evidence that can still be observed today. The expansion of space, the cosmic microwave background that fills the universe, the proportions of light elements, and the way large-scale structures developed over time. This evidence shows that the universe once passed through a state that was far hotter and denser, but it does not automatically tell us what happened at the earliest imaginable moment, nor does it confirm that time began from an infinite state. The Big Bang is best understood as the history of expansion from an extremely hot and dense phase, not as a localized explosion occurring in one particular place. When the equations of general relativity are extended backward, the density of matter increases, distances shrink, and the curvature of spacetime becomes more intense. If no new laws of physics intervene, the classical model leads toward a state in which density and temperature approach infinity, while the characteristic scale of the universe approaches zero. This mathematical state is known as the Big Bang singularity. The word singularity may suggest that science has identified a specific object or location at the beginning of time. In reality, no telescope has ever observed a singularity directly. Everything humanity can observe belongs to later periods, when light or other physical traces were able to exist and travel toward the present. The singularity appears when a highly successful theory is pushed to its most extreme limit, where the quantities, in its equations, no longer remain finite. An infinite value in mathematics does not necessarily correspond to something truly infinite in nature. Sometimes it is a sign that the model is missing an essential component. A map may describe thousands of miles of terrain with remarkable accuracy, but once it reaches an unexplored region, its final lines can no longer be trusted to represent the landscape correctly. General relativity has described the gravity of planets, stars, black holes, and the expansion of the universe extraordinarily well, but it was not constructed as a quantum theory. Quantum physics, in turn, describes the atomic and subatomic world with extraordinary precision. It explains the structure of atoms, the ways particles interact, and why matter remains stable instead of collapsing completely. Yet when gravity becomes extremely powerful within an extremely small region, both general relativity and quantum rules must be taken into account. Science still does not possess a complete theory of quantum gravity that has been tested broadly enough to describe with confidence either the earliest state of the universe or the deepest interior of a black hole. This gap leaves room for several possibilities. A singularity may be a genuine feature of nature that human intuition finds difficult to accept. It may also be only the place where general relativity is no longer sufficient, much as an equation describing a fluid cannot fully explain what happens when the structure of individual atoms becomes important. If quantum effects alter the behavior of matter and spacetime before density reaches infinity, collapse may end in a different way. The present universe already contains objects showing that matter at extreme densities does not behave like the familiar matter found on Earth. Neutron stars provide one of the clearest examples. They form when massive stars reach the ends of their lives and can no longer generate enough pressure to resist gravity. The stellar core collapses, compressing atoms so intensely that their ordinary structure can no longer remain intact. Electrons are forced into close contact with protons, and during the collapse, many protons and electrons combine to form neutrons while releasing neutrinos. The result can be an object only a few dozen kilometers across, yet more massive than the Sunday. Matter within it is so dense that even a tiny amount, if it could somehow be brought to Earth while remaining in the same state, would possess a mass almost impossible to imagine in everyday life. The neutrons are not arranged like separate marbles squeezed into a box. They exist in a collective quantum state, in which the rules governing fundamental particles determine how matter resists gravity. One of the most important of these rules is the Pauli exclusion principle. For certain kinds of particles, no two completely identical particles can occupy the same quantum state at the same time. When matter is diffuse, particles have many available states in which to arrange themselves, and this rule produces no obvious large-scale effect. But when matter is compressed into a very small volume, the lower energy states gradually fill up. The remaining particles are forced into states with greater momentum and energy, producing a form of pressure that resists further compression. We might imagine a theater in which each seat can hold only a limited number of people. When the auditorium is nearly empty, everyone can easily choose the lower rows closest to the stage. Once those seats are filled, newcomers cannot pile into the same places and must move into higher rows instead. The more people who enter, the farther upward they are forced, into positions requiring more energy. In quantum matter, there are no actual people, seats, or auditorium, but the image helps explain why compressing identical particles can create resistance without requiring heat or ordinary nuclear reactions. Quantum pressure can keep a neutron star stable against gravity, but only within a certain range of mass. Matter continues to collapse, and an event horizon forms. In the classical model, the process then proceeds toward a singularity. Yet neutron stars still offer an important lesson. As density rises, we cannot simply extend our intuition from ordinary matter. Rules that are almost invisible at low densities can become powerful enough to determine the fate of an entire star. From that lesson, some physicists have asked whether a form of pressure related to the quantum exclusion principle might become important at even greater densities. The idea is not simply to take the pressure inside a neutron star and magnify it until it causes an entire universe to rebound. Each model must define how matter is described, how pressure changes with density, and how that pressure affects the geometry of spacetime in return. Eververse, a small change in these assumptions can produce a completely different outcome. In 2025, Enrique Gastiñaga and his colleagues published a model in Physical Review D examining the gravitational collapse of a finite distribution of mass. The study considered a spherical structure contracting under gravity and introduced a transition in pressure at extremely high densities, driven by the quantum exclusion principle. Within the model, pressure does not merely increase slightly as matter is compressed. It becomes strong enough to alter the course of the entire process. During the early stage, gravity dominates, and the mass continues to contract. Its radius decreases, its density rises, and the space-time around it becomes more intensely curved. If the matter has no sufficiently powerful mechanism to resist the collapse, the contraction continues toward a singularity. But when the density reaches a certain threshold in the model, the state of matter changes and quantum pressure rises sharply. This pressure begins to act against the collapse. The inward motion does not stop instantly, as though the matter had struck a solid wall. Instead, the process can be imagined as a contracting mass slowing more and more as it approaches its smallest size. The kinetic energy of the collapse, the pressure, and the gravitational field are all connected within the equations. At a finite radius, the contraction reaches a transition point. The density may become extreme without becoming infinite, while the size may become extraordinarily small without falling all the way to zero. Beyond that point, the direction of evolution reverses. The mass begins to expand. This is what is meant by a bounce, not a ball of matter striking a surface and springing back, but a transition in geometry and the state of matter from contraction into expansion. There is no explosion traveling through space, because the space within the region itself is changing. If this process occurs inside a region where an event horizon has already formed, two observers may describe it in very different ways. From the outside, an enormous amount of matter collapses and forms a black hole. The event horizon conceals the high-density region, preventing any signal from the deeper process from returning. An external observer can continue to measure only the black hole's mass, spin, and gravitational influence on its surroundings. From within, the history may not resemble a small object resting inside a larger space. Matter and space contract toward an extremely dense state. Their motion gradually slows, and then the direction changes. After the bounce, distances begin to increase. Temperatures are extraordinarily high. Matter exists in states far removed from familiar atoms, and space expands over time. If observers appear only much later, they cannot look backward through the horizon and see the parent universe. They can study only the history of the region of space in which they live. By measuring galaxies moving apart, observing leftover radiation, and tracing the equations backward, they would arrive at a hot and dense phase in the past. They might call that phase the Big Bang, even though from an external description, it resulted from collapse and a bounce inside a black hole. This change in perspective is the most compelling part of the hypothesis, but it is also where the greatest caution is required. The fact that a mathematical model permits two different descriptions does not mean that the universe was truly born in this way. The equations show only that such a possibility can remain consistent under certain assumptions. To become an explanation for our universe, the model must reproduce what has been observed: the rate of expansion, the formation of elements, the cosmic background radiation, the distribution of galaxies, and the tiny fluctuations left from the earliest era. Another important issue is cosmic inflation. According to many current models, the very early universe passed through a period of extraordinarily rapid expansion. During an extremely brief interval, distances increased dramatically, allowing a very small region to grow large enough to eventually contain the entire observable universe. Inflation was proposed to explain why widely separated regions have nearly identical temperatures, why the observed geometry of space is close to flat, and how primordial fluctuations could later develop into galaxies. In the 2025 bounce model, the pressure that emerges at high density does more than prevent a singularity. After the direction of motion reverses, it may also generate a period of exponential expansion. Mathematically, this pressure behaves like a source capable of driving inflation, connecting gravitational collapse to a phase of extremely rapid growth. Rather than introducing an entirely separate inflationary field from the beginning, the model attempts to link the bounce and the universe's early expansion through the same effective mechanism. This does not mean that the problem of inflation has been solved. Any model seeking to replace or supplement current scenarios must produce the correct duration of expansion, the correct amplitude of density fluctuations, and the correct pattern of observable signatures in the cosmic microwave background. It must also explain how the rapid expansion ended, how its energy was converted into matter and radiation, and how this transition led into the hot Big Bang history supported by observation. The contraction and expansion can be imagined as the changing rhythm of a space with no external surface. Distances between points gradually decrease, not because everything is flying through a room toward a tiny sphere, but because the scale by which space measures distance is itself changing. Upon reaching a limit, that scale reverses its evolution. Distances that had been shrinking begin to grow. For the matter within, this would not feel like striking a shell and being thrown backward. It would be a transformation of the entire geometric background that determines how everything moves. If a bounce occurred, it could replace the singularity with a bridge between two eras. Before the transition would be a period of contraction, followed by a period of expansion. Time would not necessarily have to begin at a point of infinity. The Big Bang would then no longer represent the absolute origin of everything, but the name given to the hot, dense state that followed after the direction of evolution had reversed. However, the question immediately shifts to the period before the contraction began. Where did the original mass come from? What kind of spacetime did it exist within? Why did it collapse? Did the process happen only once, or was it part of a much longer sequence? A model that avoids a singularity does not automatically solve the entire problem of origins. It merely moves the boundary of the question into an earlier era. The scientific value of a model does not lie only in the story it can tell. A hypothesis becomes useful when it produces signs that can be tested, and when observations have the power to prove it wrong. If every possible result can be explained only after it has already been observed, the model becomes difficult to distinguish from a purely speculative idea. One notable prediction of the 2025 model concerns the curvature of space. On the largest scales, the universe may be nearly flat, positively curved like a closed space, or negatively curved according to an open geometry. Here, flat does not mean that planets and galaxies lie on a flat surface. It refers to the way straight lines, angles, and distances behave when measured across cosmic scales. In a perfectly flat space, the familiar rules of geometry remain valid on the largest scales. In a positively curved space, paths that appear parallel may gradually move closer together, while the angles of a sufficiently large triangle may add up to more than 180 degrees. These are still only illustrations, because the three-dimensional curvature of the universe is difficult to imagine using intuition developed through everyday life. Current measurements indicate that the universe is extremely close to flat within observational limits. The bounce model described above, however, predicts that there may be a small but non-zero positive curvature, corresponding to a closed geometry. If that curvature is large enough for future surveys to detect, it could become a significant clue. If increasingly precise measurements show that space is flatter than the model allows, the scenario could be constrained or ruled out. It is this ability to confront data that makes the prediction more important than the model's ability to tell a compelling story. Even so, A closed curvature would not be a unique fingerprint of a universe born inside a black hole. Other models can also produce a small spatial curvature. Conversely, a measurement very close to flat would not necessarily eliminate every form of the big bounce, because different bounce models can make different predictions. Science needs a collection of mutually consistent signs rather than a conclusion resting on a single number. Beyond curvature, researchers must also examine possible traces in the cosmic microwave background, the distribution of matter, and the spectrum of primordial fluctuations. If the universe contracted before it expanded, those disturbances may have evolved differently from those in scenarios beginning with conventional inflation. Yet the bounce itself could also erase or distort much of the information from the earlier phase, making a clear signal extremely difficult to find. A greater limitation lies in the origin of the quantum pressure used in the model. The exclusion principle is a rule that has been tested extensively, and degeneracy pressure genuinely exists in white dwarfs and neutron stars. Extending these phenomena to conditions deep inside a black hole, however, requires many assumptions. No one has observed matter under such conditions, and no experiment has reproduced comparable densities. We cannot simply say that because quantum pressure resists collapse in a neutron star, it must inevitably produce a bounce when a black hole forms. A neutron star has its own structure, composition, and physical limits. Once an event horizon appears, the geometry of spacetime is also fundamentally different from that of a star remaining outside a horizon. The 2025 model proposes a specific way for pressure to change with density, but that description still needs to be examined by other studies and compared with competing possibilities. There is also no confirmed theory of quantum gravity demonstrating that singularities must disappear. Research programs such as loop quantum gravity, string theory, non-commutative geometry, and various regular black hole models offer different possibilities. Some produce a bounce, some alter the structure near the singularity, while others suggest that the familiar concepts of space and time may no longer exist at extremely small scales. Even if a singularity is avoided, not every way of avoiding it creates a child universe. Matter could transition into an extraordinarily dense core, a stable quantum state, a different region of spacetime, or a structure for which we do not yet have an intuitive name. A bounce is only one possibility among many paths currently being explored. No observation today shows that a bounce is occurring inside a black hole. The event horizon prevents direct signals from that region from returning to the outside. Everything humanity can measure comes from the surrounding environment, from the motion of matter before it crosses the boundary, or from gravitational waves emitted as black holes form and merge. What happens deeper within remains an inference based on theory. Nor has any signal been confirmed as coming from a parent universe. If our universe truly formed inside a black hole, the horizon separating the two may make direct communication impossible. The only surviving traces might be encoded in the initial conditions of space, its curvature, its rotation, or the large-scale distribution of matter. Even those traces could have several alternative explanations. A mathematical model should therefore not be presented as though it were an exact historical record that science has already recovered. It is more like a possible path discovered within a vast landscape of equations. That path shows how a region of matter might contract without reaching infinite density, then shift into expansion and produce features resembling an early universe. But the existence of the path does not prove that nature followed it. The Big Bounce is compelling because it replaces an incomprehensible endpoint with a transition. It allows time to continue through the place where a singularity once appeared, connecting the collapse of a region of matter with the birth of a new space. In this picture, the Big Bang is no longer the moment when everything emerged from nothing, but the hot, dense phase that followed after an inward motion slowed and reversed direction. Yet a hypothesis about the origin of the universe truly approaches observational science only when the sky preserves traces that can be measured. If the universe was born from a collapsing object, particularly a rotating black hole, Might the large-scale structure of space retain a preferred direction? Are the rotational directions of galaxies distributed entirely at random, or is there a very slight imbalance extending across enormous distances? These questions turn attention toward the James Webb Space Telescope. It cannot see a bounce, nor can it photograph a parent universe. What it records is light from distant galaxies, including the apparent shapes and rotational wavelengths and rotational directions of structures that existed long ago. Some results drawn from those images have sparked debate, not because they prove that the universe lies inside a black hole, but because they raise the question of whether the sky is truly as balanced in every direction as we have generally expected. When a spiral galaxy is observed from Earth, its arms may appear to curve clockwise or counterclockwise. At first glance, this difference may seem like nothing more than a detail of shape, but it can carry information about the motion of hundreds of billions of stars around the galactic center. If galaxies throughout the universe formed with no preference in their directions of rotation, then a sufficiently broad and fairly selected sample should not lean too strongly toward either orientation. The numbers in the two groups may never be exactly equal, but as the sample grows larger, their proportions would be expected to move closer to balance. This is why the apparent spin direction of galaxies can be used as a test of cosmic symmetry. The standard cosmological model is based on the assumption that, when viewed on sufficiently large scales, matter is distributed almost uniformly and nature does not favor any particular direction. On smaller scales, this is clearly not perfectly true. Galaxies gather into groups, groups form clusters, and clusters are connected by long web-like structures. The Milky Way also has a plane, an axis of rotation, and a surrounding environment that is not identical in every direction. Only when we step back far enough are these local differences expected to blend into a more balanced picture. This assumption is not an unchanging belief that science forces the data to obey. It is a principle that must be tested through many independent forms of observation. The cosmic microwave background, the distribution of galaxies, the motion of galaxy clusters, and the spin directions of spiral structures can all be examined for signs of a preferred direction. If several different measurements point toward the same axis in the sky, the current model may need to be adjusted. If a signal appears only in a small sample and disappears when the observing method changes, the possibility of bias in the data becomes far more important. Galaxy spin is especially difficult to study because a telescope cannot see an arrow attached to each galaxy. An image reveals only how light is distributed across the plane of the sky. For a spiral galaxy viewed relatively face-on, the curvature of its arms can be used to classify it as appearing clockwise or counterclockwise from Earth. This classification usually rests on the assumption that most spiral arms trail behind the rotation of the material within the galaxy. Galaxies with leading arms may also exist, but they are thought to be much rarer. Even when the structure is clear, clockwise rotation remains a description that depends on the observer's point of view. If the same galaxy were seen from the opposite side, its apparent orientation would be reversed. Counting the two spiral patterns is therefore not the same as measuring the complete three-dimensional rotation vector of every galaxy. It is a measurement of how projected spin directions are distributed across the sky from our location. That limitation requires every conclusion to be expressed with care. The James Webb Space Telescope has opened a new possibility for this kind of work. With its infrared sensitivity and high resolution, it can reveal the structures of distant, faint galaxies that earlier surveys struggled to classify. Light from very distant galaxies has been stretched to longer wavelengths by the expansion of the universe, shifting radiation that was once visible into the infrared. JWST was designed to detect precisely these wavelengths, allowing features that were previously too faint to emerge with greater clarity. One deeply observed region is GOODS S, short for the Great Observatory's Origins Deep Survey South. This was not an entirely new area that JWST happened to select. GOODS S had already been studied by many observatories over the years, creating a rich archive of information about galaxies at a wide range of distances. When JWST directed its infrared instruments toward this field, tiny points of light that had once been difficult to distinguish began to reveal structure, including spiral arms clear enough for some galaxies to be classified by their apparent direction of curvature. A study published in 2025 used data from the JADES field within GOODS S and applied an image analysis algorithm to determine the direction in which the spiral arms curved. The algorithm did not attempt to reconstruct the full three-dimensional motion of each galaxy. Instead, it transformed the image into a representation based on distance and angle around the galactic center, then searched for the bright bands created by spiral arms. The slopes of these bands were used to determine whether a galaxy curved in one direction or the opposite. Objects without sufficiently clear detail, such as elliptical galaxies or galaxies that were too faint, were not included among those assigned a spin direction. After the selection process, 263 galaxies remained. Of these, 158 were classified in one direction and 105 inches the opposite direction, corresponding to a ratio of roughly 60% to 40%. According to the binomial calculation used in the study, an imbalance of this size would be unlikely to arise entirely by chance if every galaxy had an equal probability of belonging to either group. The author therefore argued that the asymmetry within the GOODS S sample deserved serious consideration. The numbers 158 and 105 can easily produce an attention-grabbing headline, but their meaning is far narrower than some popular accounts have suggested. They do not show that roughly 2/3 of all galaxies in the universe rotate in the same direction. To begin with, the reported proportion is closer to 60% than to 2/3. More importantly, these galaxies came from only one observational field covering a small region of the sky, and the sample included only objects whose shapes were clear enough for the algorithm to classify. We might imagine someone entering a vast forest and choosing one small clearing in which to count how many trees lean to the left and how many lean to the right. If 60 trees in that clearing lean left while 40 lean right, the result would certainly be interesting. It might suggest that the wind usually blows in one direction, that the ground is sloped, or that the trees in that area share some common influence. But it could also be a feature unique to the chosen clearing. To determine whether the entire forest follows the same pattern, the observer would need to visit many other locations, use the same measuring method, and see whether the imbalance repeats or reverses. GOODS S is similarly a very deep field of observation, but it does not cover the entire sky. Its depth allows telescopes to see extremely distant galaxies, while its narrow area limits the conclusions that can be drawn about structures on the scale of the whole universe. If a sample lies mainly in one direction, its results may be influenced by the particular properties of that region, by structures along the line of sight, or by the field's position relative to the plane and rotational axis of the Milky Way. Testing for a genuine preferred direction requires surveys of many widely separated regions of the sky. If one side contains more galaxies from the first group, some dipole models might predict an opposite tendency on the other side. If every field appears to favor the same apparent direction when viewed from Earth, researchers must consider whether the cause lies in the observing process itself. A truly cosmic signal should create a consistent pattern across position, not merely a numerical imbalance within a single deep field. The size of the sample also matters. 263 galaxies may be enough to identify an imbalance within a specific statistical calculation, but it is still a very small number compared with the hundreds of billions of galaxies that may exist in the observable universe. Adding or removing only a few dozen objects could noticeably change the ratio. Larger area surveys, independent classification methods, and selection rules defined in advance will therefore be necessary to determine whether the signal persists. Another difficulty begins with the question of which galaxies are clear enough to classify. JWST detects an enormous number of objects, but not all of them have easily recognizable spiral arms. Galaxies with high surface brightness, well-defined structure, and favorable orientations are more likely to enter the sample. Galaxies that are too faint, too small, obscured by other objects, or viewed nearly edge-on may be excluded. If the probability of being retained has even a slight relationship with apparent spiral direction, the final sample could become unbalanced, even when the underlying population is perfectly symmetrical. The algorithm used in the study was designed to operate symmetrically and was tested by mirror flipping the entire image field. When the images were reflected, the spin labels reversed as expected, indicating that the processing rule itself did not simply favor one fixed spiral orientation. This is an important test, but it cannot eliminate every possible source of bias. An algorithm may be symmetrical, while the set of input images is still influenced by brightness, resolution, object selection, or the structure of the observed field. Image quality also directly affects how reliably spiral arms can be traced. A distant galaxy may appear as only a few faint bands of light. Noise, the uneven distribution of star-forming regions, or another galaxy overlapping along the line of sight can make the arms appear to curve in ways that do not perfectly reflect their true structure. The stricter the recognition threshold, the cleaner but smaller the sample becomes. The more the threshold is lowered to retain additional objects, the greater the risk of misclassification. The balance chosen between reliability and sample size can therefore influence the final ratio. Even the human eye is not entirely neutral when viewing spiral patterns. In community-based galaxy classification projects, participants have sometimes shown a tendency to recognize one orientation more easily than the other. The way an image is displayed, the placement of selection buttons, or ordinary visual habits can all introduce subtle biases. Using transparent algorithms and testing them on mirrored images can reduce some of these problems. But the strongest results still need to be reproduced by multiple teams using different methods. One possibility proposed by the study's author involves the rotation of the Milky Way itself and the Doppler effect. When a light source moves relative to an observer, its observed wavelength and brightness can change slightly. Under this interpretation, galaxies whose apparent spin direction is opposite to that of the Milky Way in certain parts of the sky might appear marginally brighter, making them more likely to pass detection or classification thresholds. The imbalance would then not necessarily mean that the entire universe favors one direction, but could instead arise from the observer's position and motion. This remains only one possible explanation, not a confirmed cause of the 158 to 105 ratio. Testing it would require simulations of the expected change in brightness, the application of the same selection procedure to fields in many different directions, and an examination of whether the signal varies with the Milky Way's rotational axis. If an observational bias is responsible, identifying it would still be valuable, because recognizing such effects would allow future surveys to correct their data more accurately. Care is also needed when inferring motion from the shape of spiral arms. Most spiral galaxies are thought to have arms that trail behind the direction of rotation, so their curvature can provide a reasonably reliable clue. Galaxies, however, are complex dynamical systems. Their shapes can be altered by gravitational interactions, collisions, central bars, or density waves moving through the disk. A small number may even possess leading arms. If these unusual structures are not distributed equally between the two groups, or if their frequency changes with distance, determining spin direction from morphology alone introduces further uncertainty. Statistical treatment is where the debate becomes most visible. One research group may ask whether the total number of galaxies in the two orientations within a single field differs from an even split. Another may search for a dipole pattern that changes with position across the entire sky. Some use binomial probabilities, while others apply Bayesian models or simulations to determine whether a signal is stronger than noise and selection bias. These questions may sound similar, but they are not identical. So the same dataset can lead to different levels of confidence. An analysis first published in 2024 and later updated assembled publicly available datasets containing spiral direction classifications, then tested for large-scale angular anisotropies using both Bayesian and frequentist methods. The researchers found no evidence strong enough to reject isotropy and argued that some opposing conclusions depended on statistical tests that had not been chosen appropriately. Another study, examining hypersuprime cam data likewise, found no significant evidence for anisotropy or for a global ratio different from 1/2. When the researchers tested additional patterns, including dipoles, quadrupoles, and differences between the two hemispheres, the results continued to support a symmetric model. The authors emphasized that using a statistically well-founded model is essential to avoid discovering a pattern created by the analysis itself. On the other side, studies reporting asymmetries argue that some testing methods may weaken a genuine signal by assuming the wrong form for its distribution, combining regions of the sky with opposing tendencies, or failing to account for the observer's position within the Milky Way. They also note that several different surveys have reported imbalances in certain directions and suggest that this apparent repetition deserves further investigation. The debate is therefore not simply a case of one side having data while the other denies it. Both sides agree that galaxy images contain measurable information, but they disagree about how samples should be selected, how the signal should be defined, and how to calculate the probability that a pattern could arise by chance. This is common in science when the effect being sought is extremely small compared with the many possible sources of noise. If the imbalance in Goods S disappears after additional fields are observed, the original result will still have value. It would help identify the conditions that can create bias in deep field surveys, including brightness, algorithms, and the motion of the Milky Way. If the imbalance reappears in a consistent pattern across the sky, the question will become more profound. Even then, however, confirming an asymmetry in galaxy spin directions would not mean that the entire universe is rotating. A globally rotating universe is a different concept from certain regions containing more galaxies spiraling in one direction than the other. If spacetime possessed an overall rotation, it could create a preferred axis and leave several kinds of traces. The cosmic microwave background might display characteristic patterns in temperature or polarization, while the motion and distribution of matter could deviate from the predictions of an isotropic model. These signs would need to agree with one another, because a rotation strong enough to influence galaxies would be unlikely to leave no detectable trace in other measurements. The cosmic microwave background is especially important because it provides an image of the universe when it was still very young. This radiation arrives from every direction and has an almost uniform temperature, with only extremely small variations. Those faint fluctuations later became the seeds from which galaxies and galaxy clusters formed. The standard model uses the near uniformity and isotropy of the cosmic microwave background as one of the central foundations for describing the evolution of the universe. The microwave background still contains several unusual features, including differences in the signal across very large regions and one particularly notable cold spot. However, polarization measurements from Planck have not found evidence strong enough to confirm that these anomalies arise from new physics or from a global cosmic rotation. They may be related to statistical fluctuations, foreground effects, or factors that are not yet fully understood. For now, there is no consistent body of evidence showing that the entire universe rotates around an axis. The distinction between three levels of inference must remain clear. The first is an image field containing unequal numbers of galaxies with the two apparent spin directions. The second is the possibility that this imbalance belongs to a structure extending across the entire sky. The third is the interpretation of that structure as evidence of a rotating universe. Each step requires new data and may fail even if the previous step is confirmed. Suppose future surveys discover a stable dipole pattern in galaxy spin directions. That result would first indicate that isotropy should be re-examined through other observations. It might be connected to the way galaxies form within the large-scale cosmic web, to primordial flows of matter, to the local environment of the Milky Way, or to an observational bias that has not yet been recognized. Only after these more immediate explanations had been ruled out would the possibility of an overall rotational direction in spacetime become more worthy of consideration. Even if cosmic rotation were confirmed, the next step would still not lead directly to a black hole. Many black holes in nature rotate because they form from stars or other matter that already possesses angular momentum. As a star contracts, its size decreases while its rotation can accelerate, much like a figure skater spinning faster after pulling in their arms. The black hole that forms afterward retains part of the rotational character of the original matter. A rotating black hole is commonly described by the Kerr solution of general relativity. The space-time around it is not only curved, but also dragged along by the rotation. This effect is strongest near the black hole and can influence the orbits of matter, the structure of the accretion disk, and the way light travels through the surrounding region. A black hole is not a solid sphere rotating like a planet, but it does possess angular momentum and creates a geometry different from that of a non-rotating black hole. Some black hole universe models suggest that if the black hole in a parent universe were rotating, its angular momentum might influence the space forming within it. The child universe could then retain an extremely weak preferred direction, which might later appear in the motion or distribution of galaxies. This is an intriguing theoretical connection because it links a real property of black holes with a possible signature that could be searched for in the sky. However, no data have shown that this chain of connections actually occurred. An asymmetry in one galaxy sample does not confirm that the universe is rotating. A rotating universe would not prove that it was born inside a black hole. And the fact that many black holes possess angular momentum does not mean that every interior region of spacetime develops into a child universe. Each link is a separate hypothesis, requiring quantitative predictions and independent tests. If those gaps are ignored, a small statistical result can be transformed into a story far larger than the data support. The chain of reasoning would begin with galaxies in goods, S not being evenly divided, move immediately to the conclusion that the entire universe is rotating, and then use that claim to assert that the universe lies inside a black hole. The story is compelling, but it does not reflect the scientific process because it treats three unresolved questions as though they were already established facts connected in sequence. A more appropriate approach is to keep each layer in its proper place. JWST provided images detailed enough for one study to classify the apparent spiral directions of 263 galaxies in goods. Using the method applied in that study, the sample showed an imbalance of 158 galaxies to 105. Those numbers are the data from one specific investigation. Their meaning for the entire sky remains under debate. The possibility of cosmic rotation requires much more evidence. While the connection to a parent black hole currently exists only within theoretical models, caution does not make the finding less interesting. On the contrary, the true value of JWST lies in opening a region of data that humanity could not previously examine with the same level of detail. Distant galaxies that once appeared only as points of light are beginning to reveal disks, spiral arms, star-forming regions, and traces of past interactions. As the number of images grows, astronomers can study how galaxies acquire angular momentum, how their spin directions relate to the surrounding cosmic web, and whether local trends change across cosmic time. The rotation of a galaxy does not necessarily have to be determined by a shared motion of the entire universe. During the formation of structure, matter falls into high-density regions along directions that are not perfectly symmetrical. Tidal forces from neighboring regions can generate an initial rotation. Later, mergers can tilt a galaxy's rotational axis, speed it up, slow it down, or even reverse its direction. A galaxy's environment can therefore produce correlations across certain scales without requiring a single axis of rotation extending through all of spacetime. Deep observations also make it possible to test these correlations in more distant eras. Because light takes time to reach Earth, faraway galaxies are seen when they were younger. Comparing samples at different distances can reveal how the distribution of spin directions changed as the universe evolved. If an asymmetry appears stronger at greater distances, the cause might be connected to early universe physics, but it could also result from the fact that distant galaxies are fainter and more difficult to classify. These possibilities must be separated through simulations and independent data. Future surveys will need to cover areas much wider than Goods S, while still preserving enough resolution to identify spiral arms. Observing fields in opposite directions, using multiple wavelengths, and comparing automated algorithms with spectroscopic measurements could help test the result. If astronomers can directly determine which side of a galactic disk is moving toward us and which side is moving away, the direction of rotation can be established more securely than by relying on shape alone. Independent research groups will also need to analyze the same data without depending on identical selection thresholds or the same algorithms. When several different methods reveal the same pattern, the likelihood that it represents a real feature increases. If every processing method produces a different result, those differences themselves can reveal where hidden biases may lie. Science advances not by protecting a number from every possible doubt, but by actively searching for the ways in which it might be wrong. The debate surrounding galaxy spin directions is therefore not a sign that science has failed to provide an answer. It is the process by which a new signal is tested. One study identifies an imbalance, another re-examines the statistics, a later group expands the sample, and new telescopes study different regions of the sky. Through each cycle, an effect may become clearer or gradually disappear as sources of bias are removed. If the final result shows a distribution fully consistent with isotropy, JWST will still have helped humanity better understand how distant galaxies should be selected and classified. If a genuine asymmetry exists, it will open new questions about the formation of structure and the initial conditions of the universe. Both outcomes are valuable because data do not need to confirm a bold hypothesis in order to be useful. What JWST sees is therefore both specific and limited. It detects infrared light from distant galaxies, records faint spiral arms, and allows an algorithm to divide a small sample into two unequal groups. It does not see the entire universe rotating, observe an event horizon surrounding space, or reveal a parent universe beyond it. The distance between the images and the hypothesis remains enormous. The current data do not tell us that we live inside a black hole. They show only that a new test of cosmic symmetry has become possible, while reminding us that even a statistically significant result must be understood in the context of survey area, sample selection, and analytical method. This caution does not close the question. It allows the question to be asked more accurately. If independent lines of evidence one day reveal that the universe possesses curvature, rotation, and initial conditions consistent with a region of space born after gravitational collapse, the black hole hypothesis would gain a stronger observational foundation. For now, it remains a possibility awaiting more rigorous tests. But if that possibility proved true, the meaning of a black hole would change profoundly. Each event horizon might not be only the place where matter disappears from the view of the external universe, but also the unobservable boundary of another history of spacetime. Humanity often speaks of the universe as though it were an object that has already been seen in its entirety, with a clearly defined size, shape, and boundary. Yet everything telescopes have ever recorded belongs only to a finite region around us. This region is known as the observable universe, and that name contains an important limitation. It does not mean the entire universe. It refers only to the portion of space from which light or other signals have had enough time to reach an observer on Earth. The universe is about 13.8 billion years old. If space had remained still, we might imagine that the oldest light we receive could have traveled from no more than 13.8 billion light-years away. But space has not remained still throughout that time. While light was traveling toward us, the distances between large regions of the universe continued to increase. As a result, the places that emitted those signals long ago are now much farther away than the distance the light originally had to cross. This is why the present-day radius of the observable universe is greater than 13.8 billion light-years. The most distant objects from which we can receive signals are now located much farther away because the space between them and Earth expanded throughout the light's journey. This difference does not exist because light once traveled faster than nature's speed limit. It exists because distance is not measured against a fixed background. In cosmology, the scale used to measure distance changes with time. The boundary of the observable region is therefore not a wall located somewhere beyond the farthest galaxies. There is no layer of dark material surrounding reality and preventing light from traveling any farther. What exists is a limit on information. Light from more distant regions has not yet had enough time to reach us, or may never arrive because the expansion of space is accelerating. We might imagine someone standing in the middle of a vast landscape, covered in fog. Their vision extends only to a certain distance, but the line where the scenery disappears is not the edge of the land. It is simply the limit at which light can reach the observer's eyes under those conditions. Beyond the fog, there may be valleys, cities, or territories far larger than anything they can see. The person standing within it cannot observe those places, but they also have no reason to conclude that everything ends where their vision fades. The observable universe has a similar quality, although its limits are created not by fog, but by the age of the universe, the speed of light, and the history of cosmic expansion. We live at the center of the region visible to us, but this does not mean Earth occupies the true center of the entire universe. An observer in a very distant galaxy would also see themselves at the center of their own observable region. Every location has its own horizon, defined by the signals capable of reaching it. The idea of a horizon in this context is not entirely unfamiliar to the physics of black holes. A black hole has an event horizon, a boundary that prevents signals from returning from the interior to the space outside. The universe also possesses horizons related to distance, time, and the rate of expansion. In both cases, certain regions cannot send information to a particular observer. This similarity has led some physicists to ask whether the two structures might be connected at a deeper level, but the resemblance must be treated carefully. A black hole's event horizon and a cosmic horizon are not automatically the same kind of boundary. They arise within different geometries, depend on different physical conditions, and may change in different ways. The fact that both limit information merely opens a path for comparison. It does not prove that the universe is a black hole, just as the fact that two rivers both have banks does not mean they are the same body of water. An event horizon is defined by a region of spacetime from which no signal can escape to the outside indefinitely. An object that has crossed this boundary may continue moving through the interior, but every possible path into its future no longer leads back to the external region of space. A cosmic horizon, by contrast, is related to regions whose size, nor does it surround us like the material surface of a sphere. Despite their differences, both horizons point toward an unavoidable truth. An observer does not have access to the whole of reality. Some places exist beyond their ability to receive information. This changes the way a structure can be described. An observer outside a black hole and another falling within it do not share the same picture of time, light, and the paths that remain possible. In a similar way, someone living in an expanding universe can construct a map only from the signals that have reached their location. From this limitation, a bold idea began to take shape. In 1972, Physicist Raj Kumar Pathria published a paper in the journal Nature proposing that a closed universe could be described as the interior of a black hole existing within a larger space. This was not a claim that telescopes had detected a black hole wall surrounding us. It was a proposal about the geometry of spacetime, based on a relationship between a cosmological model and the internal structure of a black hole. What makes the idea remarkable is the way the same reality might be understood differently depending on the observer's position. From the outside, a large mass of matter may be collapsing under gravity. Once the mass is compressed far enough, an event horizon forms and hides the interior from everything beyond it. An external observer would see only the formation of a black hole and its gravitational effects. But when spacetime is described from within, the picture may be different. Instead of seeing a small object resting inside a larger space, an observer living in the interior might experience space expanding around them. Distances between regions could change over time, matter could be distributed throughout an enormous volume, and the outer horizon would not appear as an observable wall. This difference may sound contradictory, but relativity has repeatedly shown that different observers can describe the same process in very different ways. Time does not pass at the same rate everywhere. Distance is not an entirely unchanging quantity. An event may occur within a finite amount of time for someone who is falling, while its signals appear increasingly slow and faint to someone watching from far away. What Pathria suggested was the possibility that the interior of a gravitational structure could possess the geometry of a universe. From the outside, it would be a black hole. From the inside, it could be the entirety of space accessible to an observer. This idea does not require those living within it to see a dark sphere surrounding them. On the contrary, if the geometry were suitable, they might simply observe regions of matter moving apart within a space that has its own history of evolution. One reason the hypothesis continues to attract attention is the comparison between gravitational size and the amount of matter contained within the observable universe. For a non-rotating, uncharged object, the Schwarzschild radius depends directly on its mass. As the mass increases, the size of the corresponding horizon also grows. If enough matter is concentrated within that radius, a black hole can form. When researchers place estimates of the mass or density of the observable universe into gravitational comparisons, they find that the relevant scales can lie surprisingly close to one another. The size of its Braxae, its Braxae, its Braxinae, its Braxinae, its Braxae, its Braxae, its Braxae, its Braxae, its variable region, and the gravitational scale associated with the matter and energy it contains are not as widely separated as intuition might suggest. This proximity raises the question of whether the universe could be described as a structure resembling a black hole. However, this simple comparison can easily be misleading. The Schwarzschild radius is derived for a spherical, non-rotating object embedded within a relatively simple external spacetime. The universe is not a motionless sphere of matter suspended in empty space. It is expanding, contains radiation, dark matter, and dark energy, and has no observed external region that could serve as a background for the structure as a whole. The mass of the universe is also not easily defined in the same way as the mass of a star. In a dynamic spacetime, energy, pressure, and curvature are connected in far more complicated ways. Dark energy not only contributes to the universe's overall energy content, but is also associated with its accelerating expansion. For that reason, changing an estimated value, inserting it into the Schwarzschild radius formula, and concluding that the universe is a black hole would leave out most of the physics that must be considered. Two quantities falling near the same scale can be suggestive, but they are not evidence. In science, many values can happen to lie close together without sharing the same origin. To turn this resemblance into a convincing model, it would be necessary to show that the same system of equations can consistently describe the history of cosmic expansion, the distribution of matter, the cosmic microwave background, and the many other observations already explained quite successfully by the current cosmological model. Part of what makes the hypothesis difficult to imagine is that human beings usually picture a black hole from the outside. We think of a dark region among the stars, surrounded by a horizon, with a center hidden somewhere deep within. If the universe existed inside such a structure, intuition might lead us to imagine galaxies drifting through an enormous black sphere, with some visible boundary in the sky marking the edge of the black hole. But an observer living inside would not necessarily see that shape. A horizon is not a glowing wall that telescopes can identify. It is simply a limit defined by the paths that light is able to follow. If the observer's entire region of space lies beyond the horizon, then every instrument they build also exists within the same structure. They cannot send a detector outside and have it return with a report of the overall shape. The space around them could still appear immense and nearly uniform. Galaxies might lie in every direction. Light could travel between nearby regions, planets could continue orbiting stars, and the local laws of physics could operate normally. There would be no reason for someone on a planet inside to feel that they were living within a hole. Even the idea of a center becomes difficult to apply. In the familiar picture, a black hole has a center because collapsing matter appears to move toward a central region. But a homogeneous, expanding universe reveals no special location among the galaxies. From any galaxy, an observer can see more distant galaxies moving away. This does not make every galaxy the true center of the universe. It simply reflects the fact that distances within space are increasing everywhere. The most familiar illustration is a collection of small dots drawn on the surface of an inflating balloon. As the balloon grows, every dot sees the others moving away. No point on the surface can indicate another point on that same surface and identify it as the center of the expansion. The geometric center of the balloon lies in the three-dimensional space outside the two-dimensional surface on which the dots exist. This image helps explain why cosmic expansion does not require a center located somewhere within the observable universe. Any two sufficiently distant galaxies can move apart because the space between them is expanding. No galaxy needs to be flying outward from a central point of explosion. Space is not expanding into a pre-existing emptiness in the way an inflating balloon occupies more room inside a building. Even so, the balloon is only an analogy. Our universe has three spatial dimensions, not the two-dimensional surface of an object embedded in some larger space that human beings have observed. The center of the balloon, in the illustration, should not be interpreted as a real location outside the universe. The comparison is meant only to show that a space can expand without requiring a center within itself. This caution becomes especially important when connecting the idea to black holes. An astronomical black hole forms when matter collapses within a space that already exists. We can identify the external region, observe matter falling inward, and define a horizon around the central mass. The universe in the Big Bang model, by contrast, is not described as matter exploding into empty space. There is no pre-existing room for the universe to occupy. The geometry of space itself changes with time. The Big Bang was therefore not an explosion that occurred at one particular point within the universe. In the Standard Model, the early hot and dense state existed everywhere throughout the space that later developed into the observable universe. Every galaxy today originated from regions that were once much closer together, but no galaxy can be identified as occupying the location where an original explosion took place. This is a major difference between saying that the universe resembles the interior of a black hole and simply saying that the universe is one enormous black hole. The second statement can easily create the image of the universe as a single object already resting within a larger space, with a center, an edge, and a size that could be measured from outside. The first is more careful, because it refers to a possible resemblance or connection between different space-time geometries. Turning that possibility into a complete model requires overcoming a major obstacle. Classical general relativity predicts that matter collapsing inside a black hole will continue toward a singularity. There, density and space-time curvature rise toward infinity, while the equations lose their ability to provide an ordinary physical description. If the singularity is an absolute endpoint, then no new space opens beyond it. There is no continuing history, no expansion, and no child universe able to develop. The interior of the black hole simply leads to the point where every current description comes to an end. For this reason, the idea of a universe being born inside a black hole cannot rely only on similarities between horizons or gravitational scales. It requires a mechanism explaining why collapse does not end at infinite density. Something must change when matter is compressed to an extreme limit. Quantum effects may become strong enough to resist further contraction. The structure of spacetime may no longer remain continuous in the way classical equations assume, or a deeper theory may replace the idea of a singularity with a finite physical state. At present, none of these possibilities has been directly confirmed. Science has not seen inside an event horizon, measured matter in the region of a singularity, or completed a theory of quantum gravity that has passed every experimental test. What does exist are models suggesting that collapse may not necessarily continue toward infinity if new laws emerge at extremely high densities. It is at this boundary that the question of the universe and black holes begins to change. Instead of asking only whether the two structures resemble one another, we must ask what happens when contraction reaches a point where general relativity is no longer sufficient. If the singularity is not the end, matter may slow before reaching infinite density. If the contraction can be halted, the motion may reverse. Space that was once compressed could begin to expand, and from the inside, that process might take the form of a universe being born. That transition from contraction to expansion is known by a simple name, a bounce. What follows is a closing passage written at a slower pace, with almost all of the scientific detail removed and without repeating the explanations already given. When the night grows quiet enough, the stars appear once more, just as they did long before human beings learned to name planets, galaxies, or black holes. They do not change simply because we have asked a larger question about the universe. Those points of light remain separated by deep stretches of darkness, while their light continues traveling through space toward a small world orbiting an ordinary star. That light does not carry an image of the present. It preserves moments that passed long ago. A star may already have changed before its light reaches Earth. A distant galaxy may have undergone millions of years of evolution, while its earliest signal is still traveling toward us. The sky is therefore not a photograph of the entire universe taken at a single moment, but many layers of the past placed beside one another in the darkness. Humanity has learned to read those layers of light through telescopes, radio waves, the faintest ripples in space-time, and the motion of objects that cannot be seen directly. From these subtle traces, we have gradually discovered that the universe was once far hotter, denser, and smaller. We know that galaxies are moving apart, that black holes can form when matter collapses, and that light is not always able to return to the place from which it began. Even so, all of this knowledge has been built from within. No one has ever stepped outside the universe to look back upon its complete shape. There is no place separate from space and time where reality can be observed like an object resting in the palm of a hand. We can measure only what reaches us, then use laws tested across generations to infer what may lie beyond. Some boundaries do not appear as walls. They have no color, cast no shadow, and cannot be touched. They simply mark the place beyond which information can no longer continue its journey toward an observer. Such a horizon may exist even when no one stands before it to recognize it. For a black hole, the event horizon conceals everything that happens within. Matter can cross that boundary, but the light carrying news of it cannot return. In the universe, observational horizons also limit the region of space we are able to know. Some places are too distant for their light ever to have reached us, and there may be regions whose signals, even if emitted today, will never overcome the expansion separating them from us. In both cases, a horizon does not tell us that reality ends there. It tells us only that, from where we stand, we cannot see beyond it. On the other side, There may be nothing that present-day physics can describe, or there may still be a complete history whose information simply has no path back to us. The hypothesis that our universe lies inside a black hole arises from this very gap in understanding. It is not an answer that has already been found, and certainly not a secret recently confirmed by a telescope. No image has revealed a parent universe beyond our space. No signal has been proven to have crossed a horizon from the other side. What exists today are models, mathematical similarities, and questions that may lead to more precise measurements. Although it remains unproven, the idea changes the way a familiar question can be asked. The Big Bang may have been the absolute beginning of space and time, a point beyond which any description of an earlier state loses its meaning. But it is also possible that the early hot and dense state was only a transition, appearing after a region of matter contracted toward a limit and then began to expand. A black hole may likewise be the end of matter in the ordinary sense. Everything falling into it may continue toward a state that science cannot yet describe. Yet it remains possible that history continues within a different geometry, where what appears from the outside as collapse is experienced from within as expansion. If this were true, the birth of a new space would not necessarily be marked by a violent moment. There might only be matter compressed ever more deeply, its motion slowing within an unimaginable gravitational field, until the geometry quietly changed direction. What had been contracting would begin to expand. Distances would emerge between regions. Temperatures would gradually fall. The first particles would combine. Clouds of gas would form, and after an immense span of time, stars would begin to shine within a space that had never existed in quite that way before. The beings who eventually appeared in such a universe would not know that they had been born from a black hole. They would see only galaxies stretching out around them, measure the expansion, and follow ancient light backward in search of their past. They might ask the same questions we do, never knowing whether the whole of their reality was everything that existed or merely one branch within a far greater history. Perhaps we are living under the same conditions, or perhaps we are not. At present, those possibilities do not stand on equal ground when measured by evidence. What observation has established is the existence of black holes, the expansion of the universe, and the traces of a hot, dense era in the distant past. Everything beyond that remains near the boundary where theory is attempting to move farther than the data. That boundary is not a failure. It is where science becomes most careful. Every new measurement may strengthen a hypothesis, but it may also restrict it or cause it to disappear. An asymmetry in the sky could be a trace of deeper physics, or merely a result of how the observations were made. A very slight curvature could agree with a bounce model, but that model may not be the only one capable of producing it. An equation may open a universe beyond a horizon, but nature is not required to follow every path that mathematics allows. The question can therefore remain open without being hurriedly turned into a belief. We do not need to decide immediately whether the Big Bang was a beginning or a transition, or whether black holes are final endings or gateways into another history. Science can continue observing, comparing, and gradually eliminating the possibilities that do not fit, while the question remains long enough to guide new measurements. Far beyond us, galaxies continue to move whether anyone is watching or not. Massive stars still reach the ends of their lives, and some collapse, leaving behind dark horizons that light can never cross in reverse. Beyond each horizon, there may be nothing more than a silent ending. Or perhaps, in the place from which no signal can return, space is beginning a different rhythm of motion that the outer universe will never know. From Earth, everything we see is still only ancient light drifting through the darkness. It arrives from distances greater than any journey, carrying images of worlds that existed long before humanity appeared. Each signal brings reality into slightly clearer focus, while also revealing new limits waiting farther beyond. And as the light of distant galaxies continues to move through the darkness, we remain here, inside the only universe we can observe, still not knowing whether it is the whole of reality or merely a quiet expanse hidden beyond a greater horizon.